Okay, so let's at least talk through a little bit of the exam. So first of all, the average was pretty good. Although, I mean, my goal in this class is not to like overload you with one, either work or you know, to nail you on grades or anything. I mean, that's that's something that will happen with fair regularity in some of the later math classes anyways. But I really just want you to have to struggle through kind of thinking through some of these things. Since I'm an economics buff, I made a little logic problem in the first two that had to do with some economic terms. One thing I wanted to do was make sure that you kind of had to struggle thinking through something that you might not be all that familiar with. A situation like this, you can literally translate 100% into symbols, and then you can actually check the logic of it, even if you're unfamiliar with certain terms. That happens later on when I asked you about something called compactness. I know some of you may or may not know what compactness means, but the reality is you didn't really need to know what it meant to answer the question. Okay, so the dollar is strong, but exports are decreasing. Okay, so that was, you know, P and Q. All right. Oh man, I'm doing that thing again. Good grief. Hide names of annotators. Okay. This is the one where people seem to be having a little bit of trouble, and I went back and forth as to whether, you know, as to what to do about it, because there really is a way to read the word unless, okay, in logic. Some of you thought that you know, like an exclusive or might be the way to do it, which kind of makes sense, but there actually is. Unless actually is a rigorous logical term. Unemployment will rise unless the decrease in exports is halted. Okay. I think there was one person who came up with a good example. I can't remember if it was, might have been John Wright or somebody like that. But someone said, you know, if you are in the NBA, then you are tall, right? If you're in the NBA, then you are tall. So NBA implies tall. Does that make sense? Okay. There are rare exceptions to that, but let's just kind of accept that. So another way to say that is that you are not in the NBA unless what? Unless you're tall. Okay, so not NBA. Unless tall. Okay. So in other words, you know, P implies Q is equivalent to not P unless Q. Does that make sense? Okay. Now it's sort of like or. In some ways, unless kind of behaves like an or. Some of you went the exclusive or route, but that wasn't really necessary. Now I was wildly gentle with how many points I took off for such a thing. Okay. So what that means is what? So how would I write this then? Okay. So I have unemployment will rise unless the decrease in exports is halted. Okay. So unemployment will rise unless the decrease in exports is halted. So how would I write that as an or statement? Unemployment will rise. So, okay, so what's that? Unemployment will rise. That's R unless what? Not Q, right? Okay, which by the way, that's the same thing as not Q or R, which by the way is the same thing as Q implies R. Does that make sense? Okay. There are other ways that you could have looked at that, but that's kind of that's kind of the most basic way to look at this. Now, necessary and sufficient, right? We talked at length about those two terms. Okay. something being necessary for something else. Okay, so let me just say, you know, Q is necessary for P. That means that P implies Q. That means that you can't be having P without Q also being there as well. Does that make sense? Okay, some of you kind of got that one backwards. Now P is sufficient for Q. P is sufficient for Q. That's equivalent to P. So Q is necessary for P. That's P implies Q. P is sufficient for Q. Notice I flopped P and Q around this time, yes? That's also just P implies Q. So I think, right, a drop in interest rates will drop, is necessary for a weak dollar, okay? So that's like not P implies S, okay? Does that make sense? And what else? A drop in interest rates is sufficient to cause unemployment to fall. So that'd be S implies, what do I want here? S implies what? Not R. Okay. And this is not a, like if I take A, B, and C as my premises, D does not logically follow from those things. And again, I was very gentle on that, okay? Because some of you had sort of incorrect things in the first four parts that may have led you astray, but I was still fairly gentle with things, okay? But it is not a valid thing to conclude D from A, B, and C, okay? If you take P, Q, R, and S all to be true, you will see that that's the case, that indeed you get something that doesn't make sense, okay? So I just wanted to point that out. Any questions on that first page? Any questions? Okay. Now, I used equivalent to, weaker than, stronger than. Some of you were like, I don't know what stronger than means. Well, but I gave you the symbols, right? So, equivalent to means if and only if. Weaker than means it is implied by, okay? And stronger than means it implies the thing, okay? Now, the first letter, A, what's going on with that? There exists X such that. Well, remember existence, like the existential quantifier, that's like a giant or. Do you know what I'm saying? It's like a giant or. So like, you know, P of X1 or Q of X1 or P of X2 or Q of X2, and you can just rearrange that thing. And I'm telling you, these are exactly the same thing. They're actually logically equivalent to each other. Both of these guys, if you think about it for a minute, these go in this direction, okay? If P implies R is true, then certainly P and Q implies R will also be true, okay? You can kind of play around with some truth values with those. Here, there was really no difference. These are equivalent to each other. These guys down here, once again, the universal quantifier is a giant and. And so these two guys are actually the same. And then finally, this is the one that seemed to trip some people up. So this guy is equivalent to for all X what? Right? The negation of this is for all X, not P of X, and not Q of X, okay? But you realize if for all X this is true, then certainly there exists one for which it's true. Does that make sense? If for all X this is true, then certainly there exists one for which it's true, yes? So this thing goes in this direction. Okay, so that's how that went. Okay? Yeah. All right, down here. Now here what you had to do is you had to realize, you guys realize that P implies Q. Once again, this is equivalent to not P or Q. And therefore, the negation of P implies Q, the negation of P implies Q is equivalent to what? P and not Q, yeah? So like the if part stays the same and you go and the negation of the conclusion, remember that? Okay, if this, then this. Okay, so if I say, if I am going, or you know, if it is raining outside, then the ground is wet. What is the logical opposite of that? It is raining outside and what? Ground is not wet, yeah? If it is raining outside, then the ground is wet. The logical opposite of that is, hey, well, it's raining outside and the ground isn't wet, hello, yes? That's what the illogical opposite of that statement is, okay? So if I want to negate this thing, if I want to negate this guy right here, first of all, that there exists would become for all x, what? For all x, P of x and Q of x, okay, it's that and what? Not R of x, okay? Okay, some of you did some strange things with like negating through the implication or something, but you kind of have to think about what the opposite of the implication is, okay? Most of you got B right correctly, basically, but you had some notational snafus, okay, that I tried to correct on. Okay, all young women are athletes. What would be the opposite of that? There is a young woman who is not an athlete, yeah? There exists a young woman who's not an athlete. So you simply had to kind of translate that into symbols, okay? So basically this compact thing, this first part right here, that kind of stays the same, but the part, if you want to get the opposite of it, this is the part where you start having to negate things, the existence part. There exists a finite subcollection that contains this. And that's the part that really needs to be negated, the existence part. And what really is going to happen when you take the negation of that is that for any finite subcollection, the set isn't contained in there, right? So there's no way to actually take a finite subcollection and still have the whole set in there, okay? That's all you really had to do for that one. You just had to say, for any finite subcollection, the set isn't contained in it, okay? It's contained in all of them, this infinite collection, but any finite subcollection doesn't work, okay? So that's how you would negate this third thing. All right? Moving on. I'm not going to reiterate every single person's answer to number 5, okay? There was lots of different ones. This one, most people got this one basically right. A lot of you, well, one thing that was kind of interesting is a lot of you actually just did this. You said, well, this first thing right here, P and Q implies R. Let me just write that as an or. This is the same thing as not P and Q or R, correct? That's what the first thing is equivalent to. And then I go if and only if. Okay, what's the second thing? Not P and not R, or what? Or not Q. And then what you did is you applied De Morgan. Like, what's the negation of P and Q? Not P or not Q. So this is the same thing as not P or not Q or R, okay? If and only if, okay. So what about this other thing? If I use De Morgan on that first thing, not P and not R, what am I going to get? Not P or not R, which is just R, or what? Not Q. And do you guys see that those are literally the same thing at this point? Yes? They're literally the same thing on both sides. So clearly, those guys are going to be equivalent to each other. Yes? whatever the truth value of the one is, it will be the same for the other one. And therefore this ends up being a tautology. That was one way you could have gone about this problem, yeah, without having to actually make a truth table. Could have just gone through it, right? This was the, I guess, non-truth table, non-bang it on the head version of the thing. You kind of had to go through and think through the logic, okay? Okay. All right. Okay. So the answers to this, it was like, it was like true, false, false, true, 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 false, true, false. Okay. I won't go through the last one necessarily, but just suffice it to say, how many elements are there in A? I know that there's a lot of parentheses in there, right? But how many elements are in A? Right. So, I mean, if I can call that first thing little a, I call that second thing little b, and call this third thing right here little c or whatever, okay? There are three things in here, yes? So like, what's the size of the power set? Size of the power set of A, it's going to be 2 to the third, which is 8, right? Now, what about the size of the power set of A? Well, that's going to be 2 to the 8th, which is, how much is that? Yeah, 256. Oh my goodness, yeah? So if I go one deeper, like the power set of the power set of the power set of A, oh my goodness, that's already 2 to the 256. Do you know what I'm saying? Which is way bigger than that. And that one is even going deeper into the power set, right? And the more power sets I take, the bigger this thing is going to get. So that's why that last one is definitely false. Okay. The second to last one, the second to last one gave people a little bit of trouble. But basically, let me just, I mean, I don't want to give away the farm. I want you to think about this because it's really good. And I'll ask you about it maybe on Wednesday. Okay. But this guy right here saying that set is equivalent to that. No, here's the thing. Do you realize that there's like a single element in here? Like you have the braces right there. That set is like an element. It's a singular element. Okay. That thing ends up being equivalent to the empty set belonging to A and what else? The set consisting of the empty set belonging to A. And actually, so hang on a second. Is that right? Is that what I want to say? Maybe I'm not saying that exactly correctly. Or no. Not an element of, sorry. A subset of. This being a subset of A, and this being a subset of A. This being a subset of A, sorry. Okay. Okay, and that being a subset of A is kind of like the end of it. If that is true, what you can do is you can think about why this is actually equivalent to what's being said right there. Is the empty set a subset of A? And is the set consisting of the empty set, is that a subset of A? And the answer to both of those questions is yes. Think about it for a second, okay? So that ends up being true, okay? Now what about G? Is the set consisting of the empty set an element of the power set of A for every A? Well, no, it's not, unless the empty set is actually an element of that thing. Is the set consisting of the empty set a subset of the power set of any set minus empty set? By the way, this is sort of stupid, but this guy right here is really just the power set of U, yeah? If you subtract the empty set, that doesn't change anything, yeah? That's like subtracting 0 from a number, okay? So is the set consisting of the empty set a subset of that? Yeah, well, because the empty set is an element of that power set, yes? The empty set is an element of that power set, so the set consisting of the empty set will be a subset, okay? And most people did decently well on these other ones, okay? It's true that the empty set is a subset of every set because the empty set is not an element of that second set, right? So look, this guy right here only has a single element in it. It's this crazy looking thing right there. And so the empty set is not an element of that right-hand side. So you don't have that subset containment. Most everybody got C right, okay? And actually the last problem, almost everybody got that one right. U has 10 elements in it. So what's the size of the power set of U? 2 to the 10th. And then you could put that with any one of the 10 elements as the first entry, yes? So the total number of things is going to be 10 times 2 to the 10th, which is basically 10,240. And it's sort of surprising that you have 10,240 elements in the Cartesian product of those two things, okay? And again, I'd be happy to discuss some of this more with you if you happen to have additional questions, but that is the thrust of what's happening here. Any questions right now, right off the bat? Any questions? Okay. Well, what I wanted to do was revisit this thing that we kind of left hanging last time. This. Okay, I said Cantor actually gave a proof of another thing called the power set theorem, okay, which said that if you have any set, then the size of that set, whether it's infinite or not, is strictly less than the size of its power set, okay? Here, size of A less than size of B means that there is an injection that is a function that is a one-to-one function from A to B, but there's no surjection, right? There's an injection, there's something that's one-to-one, but not onto, okay? And I said that I wanted to revisit this part of things, namely that the idea of the proof is basically right here. And I want to revisit that, okay? And to kind of get us moving in that direction, look at this set B right here. So B is the set of all X in A. Okay, so look, somebody's given me a function that's going from a set to its power set. So it takes A as inputs, and the outputs are subsets of A. That's kind of weird, okay? A, are the inputs, and the power set of A are the outputs for this function, okay? And I define this special set B, which is the set of X, the set of inputs, where that input is not an element of its output. That input is not an element of its output, okay? So let me kind of rewrite that. I'm actually going to go and, so hang on a second. Let me do this. Let's go in a little whiteboard mode here, okay? Let's talk about this. Okay, so somebody's handed me a function. Oops, I want to write it like that. Somebody's handed me a function that goes from a set to its power set, okay? And I define the following set. B is equal to the set of all X belonging to A, such that X does not belong to its image, because after all, the images of things are sets, subsets of A, yeah? Okay, so that's how this B is defined. And now here's a little example I want you to work through. Okay, so suppose I do this. Suppose A is just, given by little a, little b, little c. What's the power set of A going to be? Okay, it'll be a good exercise for us to kind of think this through. What's the power set of A? What are the set of all subsets of A? A just consists of little a, little b, little c. What are the subsets of A. Yes. The empty set, yeah, that'd be one thing. What else? The set consisting of A. Yeah. What else? Set consisting of B. Set consisting of C. What else? Set consisting of, yeah, A, B, and C. Let's be a little bit more. Yeah, that's going to be one of them. Set consisting of A and B. What else? All right, A and C, B and C, and Colby, what did you say? A, B, and C, right? 1, 2, 3, 4, 5, 6, 7, 8 possible subsets, yes? Which comports with what we know about power sets, correct? Now, suppose I build this function, okay? Suppose I build a function that does this. It takes A to this guy, so this is what my function is going to do, okay? Takes A to this guy. It takes B to the empty set, okay? So this is what F does. And it takes C, why not? Let's go down here, okay? So in other words, what I'm saying is F of little a, what's the output? If the input is little a, the output is set consisting of A, B, yeah? What is F of little b? The empty set, okay? The input is B, the output is the empty set. What about C? Set consisting of A, B, and C, okay? Now, I want you to think about, okay, I want you to think about the following question. Now, the proof in general defines B in this way. B is the set of all inputs such that that input is not a part of its output, is not a member of its output, yes? B is the set of all inputs such that that input is not a part of its output, is not a member of its output, yes? Let me say it again. B is the set of all inputs such that that input is not a member of its output, yeah? Okay, so my question for you is, what is B in this example? Okay, you tell me what B is in this example. Just think about it with your neighbor for a couple of minutes, okay? What is B, capital B, in this example, okay? So think about that for a second. Well, what do you guys think? What's big B? Is little a in big B? Okay. So I mean, I don't know. Let's ask some questions here. Is little a an element of big B? Well, does A belong to its image? Does A belong to the output? Does little a belong to the output for little a? Yeah, well, A belongs to F of A, which is the set consisting of A and B. So does it meet this requirement? It can't be an element of its output, yes? So what do we conclude? So little a is not what? Is not in B, okay? Is little b in big B? Well, what? Little b is not a member of F of B. Why not? Because F of B is equal to the empty set, for crying out loud. That doesn't have anything in it, yeah? So what about little b? Little b belongs to big B, which is exciting. Okay, is little c an element of B? Well, does C belong to its image? Yes. C belongs to f of C, which of course is the set consisting of A, B, and C. It's in there, yeah? So does C meet the requirements to be in big B? No. So C is not an element of big B. So what's the conclusion here? What's big B equal to? Little b, and that's it. Yeah? Now notice that big B is not one of these things. Does that make sense? Big B is not one of these things. Yeah? Big B is not an image here. It gets missed. Yes? Once again, notice big B is not in that list. And that's for good reason. And that's actually what Cantor realized. This special set that he can create cannot possibly be in the image of this function. And therefore something is missed. Therefore this thing can't possibly be a, which one, injection or surjection? It can't be onto. That is, it can't be a surjection. Does that make sense? This function can't be a surjection. Well, let's think about this in general. So let's just think about this in general. Could capital B actually be the image of something? And remember I told you about the piece of paper thing? I mentioned this last time. I said, have you ever seen that piece of paper that's like the statement on the other side of this thing is true, the statement on the other side of this thing is false? You ever seen that? It's like this little logical paradox. Okay, it's kind of silly. Well, a similar thing is actually going to happen here. Okay? So my question is it possible that f, okay, so let me see here. Okay, so, oops, what in the world did I just do? I don't need this one. Let me see, I'll go right here. Okay, so watch. What's the case? F is going to be a function in general from A to the power set of A. I form this set B, which is the set of all inputs such that what? Help me out again. It's the set of all inputs such that X does not belong to its output. Make sense? We can easily define that thing. So note that, of course, I mean, this is B is an element of the power set of A, since B is a subset of A, right? It's a subset of elements of A, yeah? Now, could there exist A in big A such that f of A is equal to B? Okay? That's the big question. Could there exist something in there such that f of A is equal to B? If it's not possible, that means that this can't possibly be a surjection. Does that make sense? If nothing ever hits this set B, then we've missed something over in the power set. Yeah? And therefore, this thing is not onto. Okay? Well, let's just suppose for the sake of argument that f of A is equal to B. Okay? We're going to show that this leads to some bad stuff. Okay? So here's my first question. Is little a an element of B? Okay? Is little a an element of B? Well, if it were, think about it for a second. What's B equal to, apparently? What's capital B equal to? It's f of A. Does that make sense? If it were, then what? A would belong to f of A, yes, which is equal to B, of course, yes. But A belonging to f of A would violate this condition. That would mean the input belongs to its output, but the condition to be in big B is that you can't belong to your output. Does that make sense? A would belong to this, and so A would not belong to what? B. Right, by definition of B. To be in there, you can't be an element of this thing. Does that make sense? Okay? That's a contradiction. Why is it a contradiction? Look, if it were, that is, if A were in B, then A couldn't be in B. Does that make sense? I mean, those are two blatantly contradictory things. If A were in there, then it couldn't be in there. Now, let's ask the question the other way. Is A not an element of B? Okay? Okay, is A not an element of B? Well, then A would not be in B, but what's B equal to again? By our assumption, F of A. Stare at that for a minute. A is not an element of its image, yes? And so what would that mean? I mean, look, then it would meet the requirement of being in there. Do you see what I am saying? Okay. If A is not in B, that means it's not in its image, which means it is in B, yes? Right? Which implies what? A actually belongs to B. Contradiction again. Because look, I mean, there's this and this. They are blatantly at odds with each other, yes? Therefore, what do we conclude? So F of A can never equal B. That means that this function is not onto. That is, it is not a surjection, yeah? This is clear. I mean, I'm telling you, this is not easy, okay? It's not easy to sort of grasp what's happening here. This is a beautiful proof, I promise, okay? If you go and like think about it, go back and rewatch this or whatever, it is a beautiful proof. It shows that this thing can't possibly ever be a surjection. It's an injection, but it's not a surjection. And therefore, what can we conclude about the size of A and the size of the power set? Which one's smaller for sure? A or the power set? A is smaller, right? The conclusion is that size of A is strictly less than the size of the power set of A, okay? You can't ever have this thing be a surjection because I've located this set that can't possibly be the image of anything, okay? I think that's kind of neat, right? And so that's where Cantor went with his thinking. And this, my friends, is why there are infinitely many levels of infinity, because you can just keep taking the power set of a given set, yes? You keep taking the power set of a given set and you get infinitely many levels of infinity. Every time you take a power set, you know you get something strictly larger. It has to be because of the power set theorem. Did someone go look up the size of the number of levels of infinity? Okay, what did you get, Noah? Yeah. Okay. So what Noah's saying is, if you actually take if you take each level of infinity as an element itself and form the set of all levels of infinity, what? Say it again, Noah. It's actually too big to be a set. There's something wrong with like the axioms of set theory, or there's some kind of fundamental flaw in the axioms of set theory. That's where stuff gets a little bit weird, okay? But there are infinitely many levels of infinity. Sort of an interesting thing, okay? Infinitely many levels of infinity. Okay, so again, do you see why this is kind of like the paper flipping thing? It's like if you assume the one thing, then you end up getting the opposite. What? If you assume the other thing, you end up getting the opposite or whatever. So it's sort of a strange little phenomenon. Okay. All right. I think I'm gonna leave it there. But what we're going to do next time is we're going to start looking at number theory and cryptography. Okay. Number theory and cryptography, which will be a a good time had by all, hopefully. And again, if you turned in your test online, I put like comments online in Canvas. Like I actually put commentary in there. Okay. So that's it for now.